And I'm very glad today to be given this opportunity to talk about the basics and some of our own works on generative adversary network. And it's definitely feeling good to come back and see many familiar faces. And actually, I always treat A&M as one of my academic home, and I still have perhaps the most amount of academic friends in A&M campus. So it's great to connect and reconnect. So without any further ado, I will start my talk today. So when you told me he wants me to give a talk on generative adversary network, the GANs, I actually feel that's quite a daunting mission because I guess most people sitting here knows what a hot and crowded field this is, right? So since the first paper get published in 2014, and last time I checked Google Scholar, that paper has been cited for more than 20,000 times. So at least 20,000 papers published, 20,000 papers published on that topic in as short as 6 years. And those topics span over a doubtingly large range, from the rigorous math and optimization foundation, and also the success who critically depend on numerous ad hoc tricks. And also they definitely get its big name from many applications, from the good applications to bad applications like deepfake. So I really feel it's a challenging job to summarize all those advances in a 2-hour general audience talk, and I will try my best to do that. And the start on the start page, I put a famous T-shirt from I remember New York's 2018 GAN workshop. I don't technically own that T-shirt, but I guess this one is very famous. Yes, we can. And I think that indeed reflects the rightful attitude of this field. This is a very promising field with many arising directions, and there's a lot of things wait to be done. And I hope today's talk would become an invitation to many of you to enter this great field. So to my best effort to summarize what need to be done for a comprehensive understanding relatively, I divided today's talk into several parts. I'll start by providing the basics to prepare what is more generally generative models and why we use them. I will then spend some time to analyze the optimization problem and the algorithm to solve GANs. So go from a slightly mathematical side. And then I will suddenly change my tone to come to the empirical ad hoc side and tell you all the ad hoc smart or not so smart ideas the field has come up with training GANs better and larger. And then I will turn to the next practical problem, which is actually have a very deep theoretical background too. That is how to evaluate GAN as a generative model. This is actually a very deep question. And then I will switch back again to the shallow and the shallow and the empirical side and give you a brief talk of the various applications GAN has ever been used for. And then I will summarize what is opening there. So let me first start with the basics. And by the way, this talk is made somehow in a rush and overall in an informal style. And if you have any questions, feel free to unmute yourself and ask me questions. I may not, because I'm using my own laptop, I may not be able to see the messages raised in the chat window after I finish the presentation. I'm doing full screen now, but yeah, if you have a question, just raise your voice and we can discuss anytime. So start from the basics. So why GAN? And to answer this first question, let me first ask a more general question: what and why the generative model? So starting from the basic statistics, generative model and discriminative models are two major categories of probabilistic machine learning models. So assume we have a distribution, we have input data X and output Y, which we usually treat as labels. A discriminative model tries to model the direct mapping from X to Y called a conditional distribution, written as a PY condition on X. And for example, in a logistic classifier, that would become just become a probabilistic classifier, and we can solve that by things like maximum likelihood we're all familiar with. Generative models are trying to do that in an alternative way. Instead of model the conditional mapping, they model the joint distribution X and Y. So why we want that? I still remember when I take my class 101 on probability, my undergraduate teacher used to tell us, if you could only request one probability from a distribution that you're interested in, definitely request the joint probability because that's the best deal. Provided by the Bayesian rule, we are able to calculate almost every possible possibility we want from this distribution by being given this joint probability, including the conditional probability that you can do by marginalization and then do the Bayes rule. And beyond just this conditional probability, the joint probability could give us many things else that were deemed as useful, but cannot be accomplished by only having this conditional distribution. For example, if y is a condition on x, modeling y this conditional probability is a classification process or somehow. But if we reverse that order, this becomes another interesting task now practitioners are getting familiar with. For example, if we have the label and we want to model the condition x, the data condition on label, that becomes the reverse process, which is to generate a data sample from a specified class label or other attribute. That is called a conditional generation task, and is now very famous in GANs, like give you a class of dog and cat and generate me an image of dog and cat. That's just by simply flipping the probability term. And because of the so rich semantics of generative model, it has been unanimously agreed that if we can have a generative model, it will be greater than having a discriminative model. And actually, from people from computer vision and pattern recognition background, this has been a very well-known scientific philosophy, which has been investigated in pattern theory field for perhaps 4 decades. It's called analysis by synthesis. So I put the gentleman, the photo of the gentleman I put in the background was Professor Ulf Grenanda, a mathematical professor with Brown University, who was a pioneer in this analysis by synthesis theory. Without giving too much background, I'll just quote one sentence from the famous article called from Dr. David Mumford in Harvard University. His famous article called Pattern Theory, a Unifying Perspective. I quote his sentence here, saying, "The analysis of the patterns generated by the word in any modality, with all their complexity, ambiguity, or confounding factors, with a goal to reconstruct the process, object, and events, or process them." That is the definition Dr. Mumford provided for the analysis by synthesized background. So if I want to interpret it in my human plain language, that says, if you want to analyze something, the best way is you first know how to generate something similar. That is the philosophy of analysis by synthesis. And I think that is a very good testimony of why we want a probability generative model. So they have been bragging about, even if the generative model is extremely flexible, and just to stress that, even you don't have data X, you can still build a generative model. Generative model doesn't have to be for supervised learning. It could be supervised, it could be semi-supervised, and even unsupervised. So it is very flexible and amendable. So we could even safely say that not every statistical learning is discriminative. For example, like many unsupervised learning is hard to say that, but almost all the problems could be more formulated as a generative problem. That being said, if you look back to the history of the machine learning field, we unfortunately will find that generative modeling actually has been relatively less studied than discriminative models. That's definitely not because generative model is not great. It's because it's much harder. Intuitively speaking, if you want to build the mapping from X to Y, for example, X is an image and Y is a class label, that's a many to one mapping. But if we reverse this process, that's going to become a one-to-many mapping, like generate a photo of a dog. That's an infinite possibility, right? And in practice, the dimensionality of X is also drastically larger than the Euro dimensionality of the Y. So when you model the conditional probability, you are modeling the probability compared to modeling the joint probability, where the 2 variable dimension gonna accumulate it together. The discriminative probability usually can find a better remedy for the curse of the dimensionality, which the later will suffer. And also modeling the generative process, considering the practice of the asymmetry of dimensions and semantics between X and Y, are usually introducing a lot of ambiguity as well. So in my next few slides, I will first present a few efforts that the deep learning field has taken towards generative models. And then I will progressively go to GAN and explain why this is a great choice. So first, just on setup and notation issues for generative models. We have labels, examples, and we assume them to be labeled just without the loss of generability. We assume they are labels from, we have data X and label Y in pairs. And we want to generate your model, a discriminative model can model the mapping, and the generative model could model the data itself, which is an unsupervised generation problem. Let's just assume that. So we can solve that. The easiest way for us, as I already implied, to solve this generative modeling is to directly do maximum likelihood. It's true. And the generation process, once the maximum likelihood is done, you get the model parameters of this those probabilities are usually parameterized by a theta. You can use maximum likelihood to optimize that theta, and after it is trained, the process of generation is equaling the sampling process from this trend probability distribution P theta X. So this is a classical problem in statistics, and I will just specifically start from what ideas the deep learning field has ever used to solve this problem. The main challenge here is, without adding surprise, the typical modeling process that we are dealing with in deep network and nowadays high dimensional data like images is that this P theta X is a very high dimensional distribution, and X is usually a very high dimensional vector. Something like, even you think of an eminence image, which is a 28 by 28 pixel, 28 by 28 image that gives you to nearly 800 pixels. That's already high. And not to say ImageNet, we know what we're talking about, right? So the people has been pursuing how to simplify the estimation of this big, doubtingly large joint distribution. The first effort offered in the modern deep learning field is called autoregressive. So it comes with a simple Markov chain style method that takes perhaps oversimplified view of this joint probability. So we assume our joint probability vector X, it have, let's say, n dimensions from x1 to xn. So this X is a vector, this x1, x2 denote its corresponding coordinate. So the autoregressive deep models borrow ideas from recurrent neural network or Markov models and factorize the joint probability into such a sequential decision-making process. And you always do the next step prediction based on the past pixel in a greedy way. In this way, every step, you are just estimating a conditional probability, which you can assume reduce the probability challenge at each step. So this is presumably a good idea for language and speech modeling. Especially in language, that's almost the foundation of one foundation of language modeling assumptions. That is, there is a sequential dependency on the language, and the word you say later depends on the word you say is formal as a context. That is correct. In general, correct. I'm not going to argue with NLP researchers on that, but in general. But I want you to reflect on that. Is it really a correct thing for image generation? While language and speech both take the form of sequences, image is not a sequence. Let me demonstrate this deficient by a representative model in this category called Pixel RNN, published in CVPR 2016. So they use autoregressive model on a pixel level in a dense image. So specifically, they start from the top left pixel as x0, and then do a zigzag scanning from the top left of an image to a bottom right of an image, and treating each pixel as a coordinate in that sequential process I just demonstrated. So so first, I don't know how they come up with an order, presumably ad hoc choice. Well, definitely you could scan the image in whatever order you want. And second, I want you to reflect, and perhaps you'll agree with me. There is no point to believe an image is generated in this fashion, right? Why my bottom right pixel have to depend on the generation of my top left pixel? There is no order of image pixels. They have concurrency, and they have complicated mutual dependency, which is anything but sequential. So this totally unrealistic assumption and will alleviate the dimensionality challenge, but really didn't lead to a big success of a generation model on images. So it's no longer a popular choice in nowadays. The next example I want to introduce is a more successful example and are still studied in parallel with GANs. It's a variational autoencoder. Before I introduce the variational encoder, I want to first draw its obvious similarity with the conventional autoencoders, which is where VAEs get their name for. For conventional autoencoder, I guess everybody now knows we have an input, we have a few MLP layers, we get a botanic layer, and we reconstruct the output from the botanic layer, and we want the reconstruction to be very similar to the input. So the botanic layer, the hidden features could be viewed as a form of compression, a latent compression of the input. And sometimes those features are more generalizable compared to the input themselves, or in general, a nonlinear dimensionality reduction approach. So while autoencoder is totally a deterministic approach without adding Bayesian sense, we are able to extend this idea of autoencoder to compress and reconstruct to an implicit generative modeling and tune that into a sampling process, which motivates variational autoencoder. So looking at this autoencoder, and then you will realize how similar VAEs are resembling them. So let's go to the next page. So similar to a typical autoencoder, VAE do the following. Autoencoder will have an input layer and a few encoding layers, which by deterministic matrix multiplications, getting to latent features, and then a few decoding layers, again deterministic multiplications, and then get a reconstruction. The input and output are measured by deterministic, means the least square loss function. So what do VAE do instead to be probabilistic? Just switch the input from adding so the input output. Now, of course, we model probability. So now the input and output become random samples from probability distributions. In order to learn this probability distribution, instead of just reconstructing every individual sample, we are trying to reconstruct the distribution of the samples. That means we do not need to reconstruct the exact sample. We just need to ensure that in a population sense, the things we reconstruct look similar to the things we input in terms of distribution or KL divergence. So the encoder and the decoder now, because we focus on model the distribution, the encoder and the decoder now do not need to be deterministic. Instead, if we now consider both input and latent variables and output, they are all random variables. They are samples from certain probabilistic distributions. Then what is the mapping from one distribution to another distribution, from one random variable to another random variable? This is naturally conditional distribution, right? So this process of encoding input into the botanic features could be modeled as, so we let Z denote now the latent random variables. So the encoder could model Z conditional X, where we generate Z from the X sampled as the input. And the decoder similarly will model X conditional Z. I hope those are all straightforward. So to learn the process, we want to maximize the log likelihood of the PX function. And this maximization process, to make it easier, we will use a technique called variational lower bound or evidence lower bound elbow. So to do that, we will first enforce the marginal distribution of the Z to match some prior distribution, and that usually need to be pre-chosen. This hidden representation, as you will very soon see, will serve as an auxiliary variable in estimating this PX maximization. During the training, this len is a latent variable generated by the encoder by fitting the X samples. And during the testing, after the variational autoencoder has been trained, we will just sample from QZ and assume this conditional probability already matched this QZ prior. So the concrete algorithm was equipped with this Z auxiliary variable. With this concrete algorithm will look like the follows. Instead of directly maximizing the log likelihood of the joint probability X, we will do a very smart change of variables here by tuning the left hand first into a marginalization of the right hand by introducing the auxiliary variable Z in now our latent random variables, and then doing a very, very interesting changeable variable here by adding this equivalent term on the later. The reason why we add that is because we want this QZ term to get combined with the PXZ term. And then you were very thinking next why we want that. So because as long as we have this QZ term, we tune this integration into our expectation term of the Q distribution. So now this QZ come together with this integration and tune into this expectation. Now we get remained with the Px and Z joint distribution of the QZ, and then we use a Jensen inequality to switch this inside expectation and the outside log. And then by using the log property, we decompose into two terms. Now we could see that very nicely, these laws have a lower bound on the summation of two terms. The first term is the joint probability log likelihood sampled over the Q distribution, and the second one is as simple as the entropy of Z. So this
Atlas, this sounds very similar to in statistics important sampling.
Well, I'm sure because this was invented by statisticians.
Oh, I see. Okay.
Yeah. VAE. So VAE is not my field, but VAE was invented by Bayesian people, and the deep learning people shouldn't take the credit here.
Okay, thank you.
Yeah. So I'm not surprised at all if statisticians find this familiar. It's all tools from statistics. So we are so to train VAEs, we're maximizing this famous evidence lower bound elbow on the left. And it also could be reinterpreted as minimizing the KL divergence between the QZ prior and the conditional distribution from Z on X. So those are all great, analytical, solid, with good, well-understood optimization algorithms. But one critical fact of VAE is it will require you to have a prior QZ, and you need to pre-specify the QZ analytically. That is an important limitation, which I will reveal by the next few slides. So before that, let me first show you some empirical things. Those are some VAE results, not the most recent. I guess I got those photos from 2015, 2016 papers. So those are the generated results by VAEs. Now VAEs can do better, but to better than that, but still not on par with GANs. I'll tell you why. So the VAE compared to pixel recurrent network definitely are doing a better job. Now see that we do not have that troublesome assumption of sequential generation, and now we directly optimize the joint probability using this lower bound trick. But now the critical limitation here is now we would need to pre-specify the analytical forms for X and Z in the very beginning of the training. And usually, for the ease of optimization, we assume them to be simplistic forms, like a dynamic covariance Gaussian or something like that. I have seen Gaussian, I have seen Laplacian, I have seen gamma beta, but usually simple analytical formulations. But although that makes our optimization easier, here is a price paid. We don't really believe the real image features lie in a simple Gaussian distribution. And that overly restricted probabilistic form prevents VAEs from capturing file details and learning more from the data. There is a limitation on its learning flexibility. But VAE, I want a disclaimer here is VAE is still improving, and VAE is still an active field, very active, and interest are mainly from the Bayesian side. So after those background, let me now come to the new world of generative model, our main role today, the GANs, and tell you why this is a great choice. So I guess now people more or less all have a basic understanding what GAN is doing. So we have some real data, and we need a GAN whose generator will work like a faker or a forger, who will create something look very similar to the real data by sampling like from random data. And another critical model called discriminators. D here could also stand for detective and try to figure out the difference between real data and generated fake data. Philosophically, it's that straightforward. So GAN has been working with for not so long history, and here I'm showing you Twitter. I'm good fellow, but only after in 2018, I remember. That's only 4 years after GAN has been invented. So he queued a few papers from the very beginning of the GANs to the latest GANs by then in generating phases. Then that's already surprisingly impressive, right? From the 2014 to 2018. And if you ask me how well people can do now in year 2020, let me show you next page. That's how we can do nowadays. We could generate ultra high resolution face with unbelievably rich details in unbelievably rich diversity. And if I let me ask you questions. From all the 3 photos, could you tell which photo is a real person and which photo is not? Well, I suppose that's a difficult enough task without a trained AI. So especially, I think now to detecting GAN generated image already require expert knowledge. For example, if you, so I can perhaps suppose that there is an unnatural purple light artifact on the hair of the lady, which usually will not come up in the natural image process. So this is a fake generated image. Actually, all those 3 photos are generated by GANs. None of them is really existent in the world. So realizing that, I hope you will pay a same compliment as our Mr. President used to pay for GAN and deep learning models. And here is a Twitter. So as our president correctly cued to us sometimes, he is very kindly reminding us, you shouldn't trust the convolutional neural network, they are fake. It's very correctly said. CNNs and GANs who actually use CNN as a backbone, they are generating fake images that you can almost unable to distill. I'm of course kidding, so for sure you know. So after viewing those amazing results, let's go a bit deeper into the conceptual diagram of GANs. So GANs, again on a high level, are made of 2 models, and the 2 models together learns the generative model. So first we have the generator, which is the real generative model we target to learn. Simply put, it usually samples from a random noise distribution, and output are real data, and the output are data, let's call it X-fake, a fake data distribution. And the attempt of the GAN to make is to make this fake data distribution to be as close as possible to the real data distribution. And how to decide that as close as possible? We have another auxiliary model, another neural network called the Discriminator model, which is a classifier that is trained to distinguish the real data sampled from auxiliary real data volume and the generated data we sampled from the G. And the goal of Discriminator is to be as critical as possible, make sure I know which one did what, and the generator try to fool this Discriminator. This natural competing process arises from the zero-sum game theory when the GAN was first arise, and it can be formulated as a minimax optimization. So there are some quick notes I want to put here to help you draw the connection between GAN, what a GAN is doing, and the probabilistic notions we just put on. So this is the random noise, which the random noise are the latent vectors, which we sample from, and again generate the ambient variables from the latent variables. Here, I want you to compare this generator form with the G, whose input is Z and output is X. I want you to compare it with the VAE we just talked about. Remember what VAE did? VAE have the input data X and have an encoder to transform the data into a random latent variable Z. And the random latent variable Z is learned and regularized by some analytical prior. It further go to the decoder to reconstruct the ambient variables. So if you look at the generative model here, you find that interestingly here we do not ever have any encoding model. We will instead directly use any simple analytical distribution as an input to mimic the sampling process, and all the heavy learning burden is now deferred to the decoder part. So equivalently, the generator here is only a decoder, and there is no role of encoder in generative adversary network. We directly sample from latent space. That's a critical difference from the variational autoencoder 0.1. And the second critical difference is, although we do have the same goal, okay? We also wanted to make the joint distribution learned to be as close as to the real distribution possible as well. And our goal is to model the PX. We still have a latent variable to help us. But the first challenge is we don't do encoding, decoding, but actually we only have decoding here. And second, we do not use a KL divergence or analytical form like a variational lower bound to measure the divergence between real and fake. So because use them, you have to have parametric forms of the distributions. To avoid that important limitation, we will remove that analytical form of divergence and instead use another auxiliary model, discriminator, to classify their domain differences. So from the perspective of the generator, we are targeting adaptively learned the loss function together as my G function being learned. From the perspective of the discriminator, it is trying to learn the divergence function, but is in a data-driven way. Actually, I'll talk about how this could be interpreted in a divergence function in some idealistic case in the next part. But overall, this is a very complicated thing and cannot be fully described as a divergence function. I'll tell you first. So in most applications, we will first learn G and then throw the G and D together during the training. And then after the training is done, D will be discarded. And in most applications, we will only need the generative model. And now it did the generative task. Sampling Z, generated X, and X are resampled, essentially resampled from the same distribution of the real data. So I want to conclude. Yes.
There's a question here on the previous slides.
Okay.
So the question is.
Sorry, I'm not watching the Zoom the chart window.
Yeah, I will read that to you. The question is D will be doing near accurate classification in beginning, but then G will learn to generate more similar images to push D to confuse and bring its accuracy to random guessing. Is this what the goal is?
Well, I'm not sure if I guess that's always a game of one pursuing the other. How about I'll use my next two slides will perhaps answer this question. How about let me go first?
Okay.
Yeah. Okay. So here I'm lay out the differences between GAN and VAES again. So the GAN's learning actually is an act-critic fashion. And to answer the question just raised, GAN never have a fixed learning goal, never fix one part, never have first learn something and learn something finish and then learn something style. It's always co-learn G and D. G will become stronger a bit and D feels threatened and D will be optimized to make up for that ability gap. Then they always alternate, make up each other. And that usually done in small steps alternatively for many times. That's something like a coordinate descent style. But I will talk about the Minimax formulation in the next part of the talk to help you understand how this comes out. So this is a Minimax problem. The divergence function is learned from data. It's act-critic learning. So the optimization is extremely difficult and unstable, especially consider G and D and now neural network. So there is nothing close to convex concave. So, and again, but the good thing we gain from that is again, now only need the black box ability to sample from the prior. You don't need to have a parametric form analytically to say write out the prior. And also because of this extra data-driven flexibility, GAN can learn from data, the distribution, the divergence, and practically it provides a sharper and better generation result overall compared to VAE result. So VAE instead, I think here exists an existing trade-off. So VAE is minimizing an analytical bound with good well-defined and divergence terms, and you have a predefined target distribution of QZ as a prior. So its L-bound approximation is very established. Optimization is well understood. But the backend is you will have to know the prior as a white box being pre-specified, and sometimes most times too strong. And VAE is easy to optimize, but its generation ability is somehow restricted. It also needs to learn an encoder-decoder pair, but as acute, G again do not need that and only need that decoder. So I'll conclude my last slides by drawing explicitly link back to the general probabilistic models. So generator is explicitly learn the target distribution, but we never explicitly specify that. It's trying to model the conditional probability, and the sampling process could be done by connecting to any simple latent space you use as the input. Now it's more like used as a catalyzer, and the learning burden all deferred to the decoding function. So here we have multiple choice of this sample manifold of the latent variable C. The most common case is to use a random noise, which gives the noise to image GAN, generate some phase from random Gaussian noise, which is most familiar to the general audience perhaps. Another popular example is image to image GAN, where Z is usually sampled from a simple composed image set. And we try to map it to a more complicated and delicate image manifold, perhaps more higher resolution, perhaps more details, perhaps in another style domain. This is called image-to-image GAN, making up another important portion of applications. So it's the last reminder is it's not easy to directly get the marginalization of all of these in the GAN, and the GAN usually do not. Most of GAN papers you will not see them explicitly compute the likelihood function estimated, but there are also some works doing that, which I give you some pointer here, but will not cover as a major part of today. So also I want to point out that GAN has been developed very extensively after many years of development. So we have seen the basic version is just to have a discriminator to the output. Output is a real image or a fake image. So that's just a binary classification. But there are more and more variants that growingly use label information or supervision in more and more diverse forms. So the conditional GAN will take a label input and the label input, but the D is still only doing the same unsupervised classification of real and fake, but not taking account into class information. That was very soon remedied by the semi-supervised GAN invented in 2016, where the discriminator will not only predict real or fake image, but also predict if that's a real image, what class it comes from. Of course, it has become, it will give the D more discriminative information to learn when it tries to learn the information beyond just real and fake. It also needs to be clear about the real image features class-wise distributions. It's a stronger supervision. And there are various different forms, but they share the common idea to utilize label information to more and more strongly supervise the D, which so I think that follow the same philosophy. I just skip some details. So that concludes the first part, the background and the basics. What is a generative model? What is GANs? What are GANs competitors, and why GAN are superior to them nowadays? So the next part, I turn to addressing the most notorious part of GANs, the optimization problem and also the tricks. So we'll go to the Minimax game right now. It's without any surprise that the GANs competing process would remind of game theory and further Minimax optimization. Principally, GAN is defined by the following Minimax game. So we have the D and we have the G. So a bit more explanation here. So we usually by default, we assume D to have an output between 0 and 1, something like a logistic function or in its output, something like it. So dx will represent the D's output will represent the probability that its input x is from the real data distribution. So that is the default setting. So in order to be the discriminator to be strong enough, we definitely want for a real data x, we have its output to be 1. And for a generated data z, GZ, Z is a Latin variable. G means it passes through the generator and output something. Its probability will be 0. That's the ideal discriminator, right? So what is the goal of generator instead? Obviously, it want to fool the D and want to have the generated data to be all classified as coming from the real data. That have come to the Minimax formulation. So D want this and G wants this. D is a max per bloom and G is a mean per bloom. So I hope this gets through. And analyzing this general minimax problem is tricky. So to understand that from a restricted case, I'll introduce you a view that borrowing idea from coordinate descent is called the optimal discriminator view to analyze this optimization. So the optimal discriminator, to analyze the optimal discriminator, we first assume G is fixed, okay? So assume we only analyze this D function, assume that's our only target. Because G is fixed, we now just write G here as a distribution, G, the P and PG, and now directly use X, just to say it's sampled from the generated distribution. G is fixed, it's now a fixed distribution we can sample from, we just don't necessarily know what it is. Okay, and it does not have to be the same with a real data distribution. Here we denote as PD. So we have the loss function on the last page can now be tuned into this can now be tuned into this loss function, and we now just need to maximize the D over this, and maximizing this will give us the concept of optimal discriminator. Writing out this, just expanding the notations, we have the objective here, PDX times this and PGX times this, and all doing integration of the X domain. Now assume we have the ideal function for the discriminator, and assume there is no collapse. So every point would have its independent different value. So minimizing this integration could be turned into doing pointwise minimization on this function at every position of X. So we can, by this assumption, we could remove the integrate from integrate notion and only minimize this pointwise function with regard to X. And the goal is to have the DX function. So the remaining thing is a simple calculus, and I'll do that for you. For this F function, I'm taking derivative to dx. Notice that here dx become a variable and a functional variable, and I'm taking derivative to that. So just if that will make it simple for you to think of, you could think of dx itself as a random variable, a variable here. Okay, we only have dx as one variable. We'll take a derivative of this dx towards this simple term. No difficulty, we only have log here. So we will do the derivative, make it equal 0 by some simple mathematics. We obtained a form called optimized representation of the dx form that is represented as PDX, which is a real data distribution, over PGX plus PDX. Here, G is a generated distribution, which means if the G is fixed already, then the optimal discriminator could be written in this following simple probabilistic way. So dependent only on the generated distribution and the discriminated distribution. So so far we are all analyzing a restricted case assumed without considering the fact of G. So I greatly simplify the problem. But now soon you will see the point we do this. Now we have the representation of the dx in terms of PD and PG. What we do next is further substitute back this new representation of dx into the original optimal discriminator objective F and see how it will lead to simplify our objective. Now let's put it back to the original function here. Now we have the dx formulation, just pull it in and get this PD and PG forms here. Now we no longer have dx. We only, across the entire objective, we only have PG, PD, those two good friends, only thing we have. Now we do on the next page, on the next notation, on the next one, I change our notation. I define mx equals the average of the two distributions. Well, we as the average, so it's our average mx, and now we have this mx, only the same mx on the bottom of both terms. So then the next things are just similar, just a simple mathematics. Pull the two out, represent those as KL divergence. So actually, if you look at this term, it could be easily first decoupled into two log terms, and then be represented as a KL divergence. So after some straightforward math, we would end up with the last term. The last term will tell us a lot of things, what we are actually minimizing with regard to the two distributions. Now first look at it. We have PD and PG as the two only variables here, distributions. And our first term is to minimize the KL divergence between the real data distribution with this average distribution. Our second term is minimizing this generated distribution's KL divergence with this average distribution. They are further averaged and plus some constant bias. This is the representation of the optimal discriminator. Or in other words, this is the true loss function we are minimizing when we use are optimal discriminator. That's the last sentence, the assumption is necessary. It's a simplified assumption. So looking at this term, and since I already talked about average distribution, I guess people from statistics should already realize that this is an old friend called Jensen-Shannon distance. So Jensen-Shannon distance is defined in the following form. Between two distances, between two distributions, A and B. So the Jensen-Shannon distance divergence, JSD, is defined by the average between A KL divergence with AB average and B KL divergence between AB average. So using this very nice form, we can directly write the optimal, the GAN loss function, assuming using the optimal discriminator to be simply minimizing the JSD between the generative model, generative distribution, and the real data distribution, plus some bias. So that has eventually led to many people perhaps you have heard, GAN is minimizing a JS divergence. This is how the JL divergence come from. And I have to emphasize again that JS divergence is a simplified approximation, assuming GAN already use the optimal discriminator, which will never reach in practice. I'll come up with more details next. But just looking at this simplified JS divergence form of GAN, we will find that a very important property of GAN at this ideal case. That is, there exists at least one minimax stationary point for this minimization. What is that? I guess this is easy to think of. Just when the G distribution and the real data distribution PD are equal to each other, then I have done my job. Then I should sit back and say I have reached a stationary point, right? So in fact, if the generated data exactly match the real data, which means P at G equals PD at almost every point, then if we go back to the optimal discriminator form here, we will see that because PG now equals PD pointwise, this dx function is reduced to a constant output function, which will simply output 0.5 for whatever x comes in. So this degrades the discriminator function, means that so what does the 0.5 mean? 0.5 means it's totally confused. Same probability for being real or fake. It cannot have any judgment. So if this D become a constant output function, naturally, this will not generate any effective gradient to generate either, because whatever input you give it is the same output, so no gradient. So in the same reason, generative distribution of the G generator has no reason to change either. Therefore, PG and PD effectively reach the zero gradient point for both discriminator and generator, and therefore makes a minimax stationary point. So that's the blessing. We do have such an optimal solution we could expect for this minimax problem. But this tells us very little how practically GAN will perform. So as I keep emphasizing, JS divergence is based on we have reached the optimal discriminator. So I'll say it in another word, that is, at every step we updating generator, we are always using the optimal discriminator possible. That assumption itself is impossible in practice. So a real discriminator calculates something much more complicated. Some in deep learning call it perceptual distance. And that's hard to be expressed as Allen divergence function. That's just not. So here are more reminders about this stationary point. I always want my student, please don't just tell people that GAN is minimizing JS divergence. It's a very naive way to think of that. So the fact is that there is a stationary point never means you will converge to that stationary point. Gradients could cycle and point away from that minimal, or the stationary point itself may be unstable or not locally well conditioned. So the optimal GAN solution may be super difficult to reach and easy to flip away. And I will remind you that although I said there exists a stationary point, I didn't tell you anything about the geometry around this stationary point. You cannot even exclude the possibility that if you switch a little bit around that minimax point, you will see a gigantic increase or decrease of values. In other words, the curvature could be extremely high. And as a bad consequence of that, so the discriminator would be extremely unstable and assigns an arbitrarily large distance between the two distributions, even if you just have a single deviation from the two. So that has actually motivated numerous works of practice that try to smooth the gradient or Locke's landscape, namely gradient penalty, Lipschitz smoothness, and the famous Weierstrass laws. So practically, the generator may often overshoot some value or oscillate around the minimum, and that really happens every day. That makes GAN training very sensitive to hyperparameters like step size or so on. So to summarize the challenges of minimax optimization, and also to answer the questions raised early on about whether we always have a good D and then have a G to for that, the real training on optimization is way more complicated than that. Instead, the real hardness of training is that the G and D always need to be trained simultaneously to hit a moving target. All the idea of mathematics that GAN papers will tell you is based on every time my discriminator will be immediately updated. I'm not saying every, sorry, I use strong word, I take it back. But at least the classical papers analyzing GAN optimization and tell you it equals Jensen-Shannon distance is assuming that every step, the discriminator could be brought to an ideal state, the optimal one, and the generator is updated under the supervision of optimal discriminator. But practically, as never happened, and practically, if the discriminator is overtrained, means that the discriminator is not so good, and the generator is much better now to fool the discriminator, then it will provide incorrect information to guide the G. And if the discriminator is overtrained, means that generator is too weak. All the images generated are obviously fake in the view of discriminator. It will correctly assign everything. It will also be a disaster because there is nothing can do for the generator to improve its result further. However it changes, you have such a tough advisor on top of you, and there is no good things you could do. Whatever you do, there will be no good things happen. So that will also collapse the minimax optimization. The correct discriminator should always be a moving target being hit, consistently changing during training until we reach that real optimal stationary point, although we don't know how to do that exactly. So because of this doubting difficulty, we have significant research effort ensured on the empirical side, doing techniques, tricks, modifications, all the ad hoc dirty things. And just to accuse that, we recently also started to work on minimax optimization using meta-learning and the so-called learning to optimize field. And we have seen some very exciting progress, and we'll report in our upcoming paper. Okay, so I guess that's the optimization part. GAN optimization, it has a lot of content in the packed, and I'm only able to introduce the most basic thing. But I hope those basic things could tell you what the picture looks like. And now I'm moving away
Atlas,
from the, oh, sorry, yeah, go ahead.
Maybe right now is a good time to take a break since you finished 2 parts and you're going to start the 3rd part. Do you think?
Okay, yeah, I can. Yeah, we can do that. How about we take a 5 minutes break? Because
okay.
To be frankly, I have 3 sections left.
Okay, all right. So
yeah, hear me well, right?
Yes.
Okay, very good. Okay, now I will start to change my tone from sounding like a bit on the mathematical side to sounding totally like an empirical side. So get me will switch. So because of the many difficulty in really training a GAN idealistically, we have come up with numerical tricks, and now I'm talking about tricks. But although I'm saying them as tricks, I want to remind you that all those tricks are very well motivated. And because of the practical optimization difficulty from analysis, and many of them are built by good mathematicians, and they really work well in practice and critical to the success of GAN nowadays. So I have personally concluded the current tricks into 4 categories, into several categories. So okay, so starting from the basics, we usually just have a backbone neural network and use a gradient accent descent to solve the minimax optimization. As you can imagine, in non-convex concave cases, don't expect anything theoretically granted. So so it has to combine with all those tricks, but there is no silver bullet that can kill everything. The 4 categories I summarize as follows. So first, there are the big category of the work has realized the stability of issues even near the minimax stationary point, and they focus on controlling the overall gradient or landscape smoothness, so you don't get explode or diminish the gradient. And the second category has been trying to, instead of optimizing the whole problem from end to end, I'm doing that in a greedy, progressive way. So every time I'm just solving a smaller optimization. The third category has been whether I can find better and more optimization-friendly architectures for neural network architectures for both generator and discriminator. And the last category are more tricks maliciously, so maliciously tricks so far. I'll go through them with representative examples one by one. So gradient is perhaps the most natural thing to see if you have ever tried training a GAN by your own hands. You will easily think that GAN's gradient will immediately fluctuate from large to small and repeatedly again. So it's not, and also we have an analysis that the stationary point do not guarantee any of its local geometry. So it's really straightforward to think of we should do something to control that local stability of the curvature. So many work has been done in this field. For example, in Europe's 2017, there's a paper called Gradient Descent is Locally Stable. And they do that in a very simple way by just minimizing the original objective. So when training the generator, minimizing the original G objective plus the gradient generated by the current discriminator. So because of the discriminator's gradient is how fast it can improve, their intuition is, I don't want the discriminator to improve too fast by controlling the gradient magnitude. Because if my generator improves just a little bit and my discriminator suddenly becomes too strong, that can override any improvement my generator and refails the generation process. So I'm controlling the step of the discriminator because I think presumably because by that time, people often found the overly strong discriminator more often than overly strong generator in practice. So that's a work by them. And a similar style work also published in 2017 called Deep Regret Analytic GAN. So the idea is similar. So here I just write out the regularizer term. So notice that by default now I just write out this regularizer term plus the original objective. Let's just focus on the regularizer. So the first regularizer is directly L2 term of the gradient. The second regularizer is random smoothing perspective. The idea is given my current, given a real data, I'm trying to do a sampling around the real data. So I first sample a X from the real distribution, and then do a random perturbation of the real distribution within a sigma ball of radiance C sampled from a Gaussian ball, norm ball or something. So this random sampled distribution. So for my random sampled neighborhood, the gradient generated at those random sampled neighborhood point all shouldn't be too large, as enforced by this expectation. So the idea is to put a stronger regularizer than the last page one. The last page one just look at the current point, and now I'm looking at the whole neighborhood, and I want to smooth out a region, not just at this current point, but also a small region nearby me. That's a stronger random smoothing regularizer. And then the next one is, I think, more practical and still in use. It's called hinge loss, or invented by the paper called energy-based GAN. So the idea is to replace the log likelihood. You remember we by default formulate again using log because that gives us smooth gradient probabilistic form and lead us to KR and Jensen divergence. Very good theoretically. But that loss function, the logistical exponential functions, family of functions have that well-known problem of the gradient issues, sometimes saturating, sometimes exploding, depending on what you use. So they instead here replace the logistic style loss for nonlinear function into a hinge style loss function. For this D, we directly minimize its value. We directly put the expectation on its value without going through P. And for this one, the same. But instead, we use a hinge here. Well, we would enforce this function value to be smaller than M. Otherwise, it will be upper bounded by this positive chain. So that have tuned this two nonlinear log functions into two linear part, relatively linear part. Here it's a piecewise linear. So this one means if it's smaller than this terms means if it's positive, then directly output this value. If the inside is negative, then output 0. So if you draw out this function, this become a piecewise linear function, something looking like a ReLU enforced on the linear function in between. So that has greatly simplified the gradient property or the gradient property. So now you can see that when you do the gradient descent, you are no longer dealing with the log stuff, and you have you are a linear function and definitely give you well conditioned gradient compared to use log. But the price you pay here is this loss function are no longer easily interpretable as a divergence theory. It's definitely not lead you to JS divergence or something similar. So it's used as an empirical trick, but with a good property that to avoid either squashed or explode gradients. Okay, so the next page, I will introduce one big player in this field. I guess people more or less heard about that. It's called Weierstrass scan. Also invented in 2017, it was widely considered as a beautiful balance between theory and application, and I think one of the superstar papers of that year. So to summarize the Weierstrass scan, simple idea, just to replace the JS of the KL style loss with a Weierstrass loss, which I will introduce next. But let's first ask a question. What's wrong with KL divergence or JS divergence? Why I'm having problem with that? Why yet another new loss? So let me first give you a very, very simple, tricky example where the deficit of KL divergence will be manifested. Just look at this simple example. Let's measure the distribution between P and Q. And P and Q are just a Dirac distribution. The real data, let's assume P, let's assume P is a point mass at 0, a Dirac. And the generated data, the fake distribution, is another Dirac distribution at a point theta. So now let's look at the KL divergence between the two distributions with regard to theta. If the theta doesn't equal 0, we just simply put together the probability because this is Dirac and the integration is just 1 point, right? You will easily see that this probability will give that infinite because now Q0 will be 0. The fake distribution will be 0 or any other point other than the theta as other point. But if theta equals 0, this distribution become merged and all the Px and Q will become 1 and this gives us 0. That clearly manifests the possibility that KL divergence could give you very ill-conditioned gradient. So as long as theta is not 0, even that's 0.001, moving from that step to theta equals 0 will require an unrealistic change from infinity to 0, and that becomes no differentiable. And in practice, although we don't often meet extreme case like that, it's very common that we don't have a smooth measure over our loss landscape, and the gradient will see very drastic instability due to the non-differentiability or close to non-differentiability at some local change steps. So next, KL divergence is not so good. How about JS divergence? Well, that save that in some sense. So let's redo the JS divergence game with this simple distribution, P real data and generate two sparkle distributions. And again, simple math. We will find that the JS divergence somehow look better at the theta doesn't equal 0 because now we are not directly comparing those two distributions. We are comparing their average distributions. That cures the problem. We put a 0 on the bottom, and now we have at least a finite function value of log 4. But still, that doesn't change the fact that when theta becomes 0, this loss will immediately drop to 0. So all the argument I just said still apply to JS divergence, not the deal. Then why Weierstrass distance? So first, let's look at what is Weierstrass. So Where's thrust distance is defined in the following way. That is, so I think formally or informally, that indicate we have two distributions. Okay, now the notations. So assume we have two distributions, PR and PG. We compute their divergence. And we use this pi to denote the joint distribution of the two distributions. So PR and PG will each be the marginalization of this joint distribution pi. So I'm sampling from this joint distribution pi. We get a pair x and y each time, and I compute x, y distance, and I compute the expectation of all the possible sample pairs. That is Where's thrust distance. That doesn't look perhaps it doesn't look immediately interpretable from one sense. But if you change it, change another view to view that, this actually means what? This actually, let me change another way to describe that. Just assume PR as one pile of stuff and PG as another pile of stuff, that two piles of masses. So now I'm trying to move all stuff in the pile PI to the other pile PG, who is currently empty. I'm trying to transporting them. I'm transporting the mass, all the mass from the PR pile to the PG pile. And now this expectation could be interpreted as I'm trying to estimate the minimum possible cost I will need to pay to transport all my stuff from PR to PG. And I'm already using the word transport because I'm actually just saying the story that optimal transport theory will tell you where the Where's thrust distance comes from. So in short, this Where's thrust distance, sometimes called Earth mover distance, defines a cost for the optimal transport plan if I want to make the PR distribution to be shifted, to be moved, to be rephased like the PG distribution. That is the intuitive understanding of Where's thrust distance. So now let's take this distance and what Where's thrust look like. Where's thrust distance is in general a headache to compute, but in the Dirac case, that's an interesting simple. Because we only have 2 points, okay? In order to move the stuff, so the point theta from point 0, we just move everything, right? Just directly move. So the Earth mover distance is all the stuff itself, the total theta. That become a beautiful thing to have, right? The Where's thrust distance now is linear with regard to the amount of the theta, the different distance between the two Dirac distribution along the x-coordinate. So if we do a differentiation over the theta, it have a constant gradient and it's smooth when theta goes towards 0 with regard to Allen direction. So that is a beautiful, differentiable, smooth, and gradient-friendly loss in this special case. And I can also tell you this is in general true in real-world functions. Although I don't want to spend time to do the math now. Here are the visualizations where we get when we compute the Where's thrust distance versus the GAN discriminator loss in a practical trend GAN between two Gaussian distributions. So while the conventional GAN discriminator will give you a divergence function change like this, a drastic change still appear. Where's thrust loss here will give you a very smooth nonlinear function where you see the gradient can be fractally propagated. I will omit the math, but I'll tell you in general, Where's thrust function give you a smooth measure space. Okay, so with all the beautiful things, looking at this function, I guess you will agree with me, it won't be such a joy to solve them or such an ease. The Where's thrust function is in general hard to solve, and we don't have the luxury to just move point from one to the other. But a beautiful technique to solve this intractable technique comes from the prime dual theory. We use a technique called the Kavitovich-Rubinstein duality, which I don't cover in this talk, but you can find the whole derivation in that paper to transform the GD loss from that infer term into now just the two expectation terms by utilizing the duality gap. But although I don't want to cover the math here, I want to cover one important necessary condition or assumption of using this Rubinstein duality. I'll just directly pass the message to you. That is, to use this duality to convert this intractable Where's thrust distance into this dual form LGD loss. you will need to assume the discriminator of the discriminator function D to have a bounded ellipsis constant. That is the condition, and you're welcome to check the paper for details why. So let's first assume that is true, then we have to ensure this is met when we apply this duality trick to convert into a tractable loss. So the original WGAN paper doing that in a, in a somehow ad hoc way. So they just do that by weight clipping, by constrain the element-wise magnitude of the weights. That somehow empirically lead to the desired effect. But I want you to remind that this is extremely ad hoc and usually at the price of sacrificing the model capacity. And practically that limits the discriminator's performance when it scales large. But Weierstrass laws already pointed to a great potential of the GAN field. That is, first, we should change our loss function to make the landscape smoother. KL is not the best thing you can do. And second, a price you pay for, not the price, a prerequisite you want to have for this smoothness. And in general helps GAN training, which is also consistent with constraining gradient in all the previous works, is you want your discriminator function to be ellipsis smooth. That's an important take-home message I want you to take from this Rubinstein duality trick, although we don't have the mask here. That inspired many people and many works, the ellipsis continuity in GANs. So immediately after, perhaps 3 or 4 months after Weierstrass GAN was invented, a follow-up paper come up in Europe of that year called Weierstrass GP. GP denote for gradient penalty. Instead of using the simple trick of clipping weight magnitude, they directly enforce the gradient of the discriminator, utilizing the property, the famous property in continuous function that if a differentiable function is one ellipsis, then it's equivalent to saying that's both sufficient and necessary to say it has a gradient with norm bounded at most 1 everywhere almost. So that's a famous conclusion in ellipsis continuity. And utilizing this property, we are converting the ellipsis constraint into a gradient constraint at a sample point. And that leads to the gradient penalty term, which you can see that we are basically trying to say wherever you sample the point, the gradient should be bounded, and gradient magnitude in terms of L2 term norm shouldn't be too far away from 1. So that's a relaxation though. So this is a very strong practical performer and still among the best competitors nowadays. It basically replaced the original WGAN with weight clipping, and now I think it's a default implementation when we talk about the WGAN. It's a better alternative and scale up WGAN to the much deeper G. For example, if I don't remember wrong, it's the first generative adversary network who can work with a super deep backbone like ResNet 101. It's a big step forward. Another important step forward is the iClear 2018 paper called Spectral Normalization GAN. Again, from the same philosophy of constraining the ellipsis continuity. It is based on the fact that the ellipsis of constant, although precisely it's very hard to compute for a deep network, it has a relatively loose upper bound. That is, for a multi-layer perceptron, its overall ellipsis constant could be upper bounded by each layer's transformation matrix spectrum norm and multiply together. The upper bound is you compute each individual linear layer, individual layer, which is or equivalent to a linear matrix. So you compute the spectrum norm for that linear matrix layer-wise and multiply them together. This is an upper bound of the ellipsis bound, or ellipsis of any neural network. Although practically this upper bound is very loose. So so to compute each layer's ellipsis function, it usually ellipsis, even that's a linear function, usually that will take SVD, which is still not so practical for deep network. To accelerate SVD computation, to approximate SVD with much faster speed, practically in SNGAN, we use a power iteration approximation to fast compute the largest gradient, the largest eigenvalues. Because anyway, Lipschitz constant is upper bounded in a linear function. Lipschitz constant is just upper bounded by the linear multiplies the largest eigenvalues. So we just need to run a few iterations of power iteration and compute the largest eigenvalue, and that's it. Just multiply all the layers estimated largest eigenvalue together, and we get a loser upper bound for the whole Lipschitz, but that's still, well, that's still an upper bound you can use. Then what the spectral normalization do is to use this total estimated layer-wise spectral norm, Lipschitz constant, to renormalize each layer's weight by directly divided by it. So the result would be, because you divide by your largest eigenvalue element-wise. So now after the division, the new matrix will at most have Lipschitz constant 1, because it renormalizes the eigenvalues, right? Easy to think. So if you multiply all those together, the whole network's Lipschitz constant cannot be larger than 1 either. That is the upper bound. So it have led to impressive generation effect, but it is also overly restrictive due to the upper bound being too loose. And now we still have there are still more papers coming in improving the spectral estimation in GANs, and just to make this regularized work better. We also have some work in Europe's 2018 discussing how to do those estimations. Okay, so I have done with my first big part. That's all about the smoothness and gradient control. We talk about directly penalizing gradient, and we talk about Weierstrass laws, which do that from loss landscape perspective. And that had again motivated back to enforce gradient penalty and continuity. And from those, I hope you can see a big picture how smoothness have played in improving GAN training stability. Now I'm coming to the next part, which is more engineering. I guess many engineers will agree with me that the best, if we have a big task we cannot complete, we just break them into small chunks and do them together and leave them work, whatever they will work like. And people in GAN has been used the same philosophy as well. So one classical work, early work in GAN is called Laplacian GAN in 2014. And it borrows the idea from image processing called the Laplacian pyramid. So specifically, Laplacian pyramid is a perception theory and analysis theory to say that image could be, so that's something that may remind you of multi-layer wavelet decomposition. So something like you have, for any image, you could decompose it into the first high frequency texture layer and then to a first low frequency layer. But the first low frequency layer, if you can be again viewed as the original image and redo the decomposition into high frequency texture and low frequency content and redo that until the end. This is called the Laplacian pyramid analysis, and it's strongly motivated by the multi-scale frequency response theory of human vision. Now, okay, call back again the analysis by synthesizer theory, and it's recognizing this interesting symmetry between analyze and synthesize. We are just, this Laplacian GAN is just reversing the process, take advantage of this theory and redo from the other way around. Because I want to generate, I will start by start by the smallest seed image, which is usually as small as a 6x6, 8x8 small images, some seed image. And I will use that seed image to hallucinate textures and to be added together with this seed image to become the next level image. And this next level image becomes the seed image for the next level again, and rehallucinate its own high texture images and reverse the process until I have reached the ultimate goal. This leads to a block-wise generation strategy, and gradually, step by step, we have seen images with sharpened and enlarged image quality. This is a pioneering work in progressive training. And later on, another major success was reached by NVIDIA after 3 years called progressive GAN. They have successfully extended this idea into training really deep GANs in really high resolution images. So the idea is, again, I start with a very shallow generator, maybe one layer, maybe very shallow discriminator, and ask them to generate a very low resolution small images. After this job has been done well, I will add a layer to generator, add a layer to discriminator. Note that I always try to keep the power balanced between generator and discriminator, and ask them to generate some slightly higher resolution images. Like this one may be 4x4, this one may be 8x8. And I can keep do that. So one layer for this, 2 layers for 8x8, maybe 3 layers by 16x16. I keep pushing that by adding more and more layers, while always keeping the symmetric power between G and D functions until where I can generate images that reach thousands by thousands pixels. And here are our end result. I think this is a nice adoption and improvement of the Laplacian generation strategy. And the key point in progressive training is to decompose the image generation into multiple resolution scales, and further always keep the generator and the discriminator to maintain a balanced and fair power. So that's it, progressive training. The third step is relatively simple and recently disputed, somehow disputed until recently. So deep learning people, you know that many deep learning people published before 2018 are just modifying deep learning architectures here and there, add a filter, decompose a filter, add some skip, blah, blah, blah. But in GANs, this has been much less popular historically. And I would say presumably because of the training difficulty. So people don't have that large room to play those tricks and the newly created building blocks. So I quote 2 influential papers by Google Research in NIPS 2018 and ICML 8 and ICML 19. They are basically saying that by using the conventional ResNet structures, most of the architectural variation doesn't seem to help by their large scale study. So actually, I remember when I go to give a talk in Google winter 2019, they told me that they don't really believe adding architectural optimization could substantially improve the GAN structure, which by that time I humbly disagreed. And then after a few weeks, a few months, our group come out the first paper proving this is indeed true, that the backbone architecture matters for GAN too. So we are the first to introduce neural architecture search to automatically optimize the architectural backbone of a generator and a discriminator. So this aligns with the trend that people commonly believe in CNNs that better architecture leads to better performance. So we have introduced NAS to the unstable training of GAN and successfully made it work. And the results are very encouraging. For a long time, I think now the rank may have dropped because the paper was published 1.5 years ago. Now many new models have come out. For a long while, our AutoGAN model, our new optimized architecture, which we dubbed as AutoGAN, has been one of the leaders on the CIFAR-10 image generation task. This is a third-party leaderboard and ranked, I remember, hundreds of leading GAN models in this field. And for a long time, as I remember, we are ranked top 1 in CIFAR-1 in terms of FID, and the top 2, top 3 on the top 2, top 3 in inception score, something like that. And in all neural architectural search method, we have been #1 for a long while until recently being taken over by some CVPR 2020 works or something. So I think that's particularly encouraging considering like those big companies, Facebook, Google, and NVIDIA has devoted numerical resources to just try and get better. And we now as a pool academic group can show them that by just optimizing architecture, we could override some of your advance as well. So we are feeling good about this work. So I'll spend 2 more pages to talk about the other empirical tricks. So all those may sound like tricks, but I will give you some idea about the intuition behind. So the first trick is called feature matching, proposed in NeuralPulse 2016. So the main idea is they claim that by just asking the discriminator to output a probability is not a good statistical footprint of the generated image. Because the image is too high dimensional, just to produce a scalar of probability between 0 and 1 is a rather poor summarization of how good that image is. So they instead claim the discriminator could make a multi-dimensional output, for example, using hidden features as a statistic of summary of the generated data. So that should contain more rich information to compare compared to just using just measuring the divergence between two scalar probabilities. So it has under two loss function regularizers where we enforce that well the generator instead of well besides just enforcing the typical divergence on the output level, that will also meanwhile enforce the feature map consistency between the generator, so the feature map response to be similar between the generated samples and the real samples. That's actually a very familiar idea to practical deep learning people, but for GANs, I think that's still new by that time. So the discriminator are also trying to maximize the same loss as well. So overall, we just added a battlefield to them. They not only wanted to battlefield on the battle on the dimension, they also wanted to battle on the feature map distance. So the next trick is proposed in the same paper. It's also a new famous paper called Improved Technique of Training GANs by Google, called mini-batch discrimination. This is actually a smart technique I really like, and it reveals an important pitfall for training GANs. So what they do is simply, instead of just let the discriminator make a classification, so once at a time, they will feed real or fake images as small mini batches and ask a discriminator to do a group classification, whether my current group of input are real or fake. The reason for doing that is they believe multiple input could give the discriminator more reliable information to summarize. They are all, because we assume they are either all real or all bad. So multiple input can certainly become more reliable and less noisy in the prediction. And an important artifact they use to motivate the work is looking at one sample per time really cannot reveal the collapse phenomenon when you try to do distribution matching. For example, if you every time you just look at 1.1 or just look at one image sample, then something will look like then the following. Let me just describe you a tricky scenario. Whatever input you give to the generator, random noise, the input or the generator will only output one similar image, one same image, and assume that image is very realistic. And the discriminator will be totally fooled by that, because every time I'm seeing a very realistic image versus another realistic image given by the real world. They should be indistinguishable, and from discriminator's view, the job is done. They are very similar, but this is not our goal, right? We don't try to generate a model to just generate one image. So we have to take into account the diversity of generation, whether the sampled distribution has seriously collapsed into consideration. Mini-batch discrimination was one of the early empirical tricks developed to address that collapse issue, because now you have to compare on a mini-batch of data rather than a single point of data. If the mini-batch of data collapse to just one similar point, those can be figured out. But we are talking in a later section how it has been treated further. Okay, other tricks on this page. So so historical weight averaging, because we already know that the gradient in GANs are highly unstable. So besides all the smoothness we have used, we also use an empirical trick where we will temporally average the weight along the training trajectory. And apparently, it's equal to some historical temporal ensemble that will smooth the parameter space, equal to enforcing a moving average to be close to the current one. So that's still the moving average way is still popular in current day trends. The most effective way is called exponential weight average, short for EMA, and that's still a standard. So we also have some other label smoothing technique and batch normalization technique. I'll just skip due to time concerns. And I'll go to my next part, how to evaluate GANs. So far I have been talking about a few representative tricks, but let me give you the reminder that GAN tricks has been invented every year, almost every day, and many of them constantly involve ourselves. And I just recalled myself in the beginning of this section, there is no silver bullet, and the practitioners try from different things. because the real optimization is too difficult. So my section 4 is a bit unique to GANs, which people perhaps don't talk a lot if we talk about general deep learning. How to evaluate? If that's image classification, one sentence answer, right? Give me a test set, I'll tell you the accuracy. But for GANs, that's a different story. For example, if you just want to generate images from noise, that's not directly quantifiable. It's an unsupervised problem. It's not like a task, like correctly label the images and I know what label it should be assigned to. This learned distribution is implicit. Our real goal is the learned distribution should be close to the given distribution. But because unlike VAE, GAN never have an explicitly parameterized form of the distribution. We have no idea that there is no direct way to compute the likelihood not to say the divergence. So how to do that? There are two mainstream ways, using human perception study or use a sampling-based method. Human study is relatively straightforward. As long as you have money to pay AWS, just do your human study. So this is a paper published in Europe last year from Stanford, from Professor Feifei Li's group, who are particularly well at collecting data set and doing human studies. So they have built this benchmark called human error perceptual evaluation of generative models, collecting I think more than tens of state-of-art generating models, the generated photos, and ask AWS workers to rate well, they use pairwise rating protocol, but the goal is to let them differentiate which can have generated more realistic looking images. The study is designed in a more delicate way, but that's the goal. So looking at all the images, so first, I guess you will feel they almost look very realistic. But from my perspective, some still have differences. For example, for the relatively worse GAN generation capabilities, they usually cannot take care very well of the background region. If you look at this background, or this gentleman's background, or this background, those backgrounds look clearly distorted if you pay some attention to them, right? They don't look like any coherent object. So that's because the background compared to the faces contain a much more spreaded and diverse category distribution, and GAN is unable to model such broad distribution. Face is a relatively focused subject. And looking at the background could help you relatively differentiate between good GANs and bad GANs. And for example, this lady, there is another whoever's face on the side, and looking at this whoever's face, you will find the shape and the geometry look unnatural. That's also an artifact of the GANs. But you have to admit it takes some professional eyes and look at a relatively long time to see the difference, right? So that also makes this subjective study relatively time and money consuming, but Stanford get it out. So they come out with this benchmark and give the subjective square to all the recent developed GANs. And they indeed show that some recent GANs, like style GAN, can already become statistically indistinguishable, become with real data in this specific task of generating human faces. So this is a very tedious task, and I don't think how it could easily generalize to new models. But still, I think that's a good effort and help understand how well our GAN is already been doing. But yeah, for us publishing daily papers, we cannot conduct that for every paper, so we go to sampling-based automatic method. There are several important dimensions to evaluate GANs. I'll introduce them briefly. So the first dimension is, of course, quality. If you generate me something close to random noise, I will not take it. So the most classical metric here is called inception score. It does the following thing. Assume I will apply a pre-trained image classifier, like a VGG classifier, on top of a generated image, and measure the confidence. Well, you're just the entropy of the softmax vector of this image, of this pre-trained model output. The philosophy behind that is, if you generate something like a natural image, at least my already trained image classifier should have some clue what it is, better clue compared to give me a random noise image. So by looking at the entropy as a proxy of the confidence, I can differentiate the really bad images from the okay images. But this philosophy, of course, is flawed in many aspects. For example, deep network classifier would have no idea if you are generating something it has never seen before, a different class, an unseen category, new object. And also softmax entropy as a really bad and uncalibrated measure of the real Bayesian confidence. So this is just a proxy. I'm not overclaiming that. But besides all those statistical pitfalls, the inception score has another important missing dimensions that it cannot support for you. That go back to the example I just mentioned, the diversity. If my generator becomes such a sneaky guy that will take whatever noise and output the same image, the same high quality image, I just want whatever random noise you give me, not just tell me whether inception score will work or not. No, because it do a sample-wise classification, whether each sample look realistic or not. It does not take into account any population level generation quality, whether it's diverse or not. It has totally no idea. So for the diversity of the generative thing, you need to do population level testing. And the most famous metric here is called a Freitrate inception distance, short for FID. IS and FID are arguably the most common metrics in GANs. So FID do the following. It models the distribution of image features, both from real and fake images, using a multivariate Gaussian distribution. So we will fit two GMM models on the generated image and the real image. And we then will compute the divergence between the two fitted GMM and use that divergence to show how close my generated distribution is to the real. That is significantly better, but also significantly costly as well, because you need to first sample a lot and fit GMM and compute divergence. So it's also significantly better, but significantly more expensive than the inception score. The good thing about it is now if you have a significant collapse of the learner distribution to just a few points, FID can detect that because you now cannot effectively fit GMM. But the FID also have its important limitations. For example, multivariate Gaussian in practice is really not a that good assumption for how natural image statistically distribute. It's just simple. So using multi-Gaussian invariant fitting itself will sacrifice some feature quality. And in practice, we commonly observe FID fails in detecting some not so serious mode collapse. Like if there is overall they look okay, but in some local part of the distribution they look very dissimilar to each other, FID cannot effectively detect that due to the impreciseness of GMM approximation. So what's next? Going beyond the IS and FID, there have been many more works, like birthday paradox text that's developed by Sajiv Arora's groups in Princeton, dedicated as detecting local mood drop. There has been classification metrics by quantifying by using another pre-trained classification model on conditional generation to detect whether some class has been significantly under-generated or over-generated, but that requires labels. And recently, my PhD student Zhenyu Wu also did a very good work called black box diagnosis. So it's also used introduced an unsupervised hypothesized testing method in the GAN generated distribution and use MCMC to compare two distributions. It's under revision, and I think that's an advanced idea. But even with those progress, there are many aspects that remain untouched yet, and there are exciting research directions. For example, all those generations cannot give you a hint how novel or how creative my current GAN is. For example, to fail both IS and FID and all those metrics, I'll just give you a tricky example. What if I'm using a gigantic GAN that is capable enough to memorize all the training set, and now whatever you give me the real image. Hello? Did I get a question?
Oh, no, go ahead. I think it's a noise.
Okay. So if my generator is ideally memorizing the entire training set, and just randomly output a training image once it's queried by a random noise, then what will happen? IS will be happy because every output image is high quality and semantically meaningful. FID will be happy because on population level, you just output the whole same training set, so no problem at all, perfect, right? But that's not what really we want GAN to do. We want GAN to be creative. The fundamental function we want GAN is resampling, not memorizing. And the current metrics are still in shortage in depicting that resampling or creative property, and we are still trying to extend that. Also, more subtle covariant reshift consistently pose challenge for GAN-based generation evaluation, and that correlates to many private issues like whether some faces, maybe some demographic group has been underrepresented in the generated images, or maybe some faces has been over-memorized, causing privacy concerns. Those are all practical problems and we not satisfactorily addressed yet. Okay, thankfully, I have finished all the perhaps the hardcore part of my talk today, and I'll leave my last part to be the amusing part, look at the fancy applications, and I promise you no math will, well, no, there will still be some math, but there will be relatively fewer math in the remaining slides. For GAN applications, I suspect many of you first by knowing GAN's application, by knowing there exists some deep learning model who can make your headshot look like a Van Gogh's painting. That was done by an application called neural style transfer, and now the standard method is powered by GAN and a specific model called CycleGAN. So it's a very creative creative invention. This is a very creative algorithm. Basically, for GAN, the task here is a image-to-image translation, saying my generator take as input an image from a source domain. So my Z is now an image, and my output X is another image. Both X and Z are natural images. They just come from different domains. So eventually, I'm doing domain conversion or domain translation. CycleGAN using the following beautiful idea. So the naive idea encoder-decoder would just be, let me train from the source domain, train such a generator to map from the source domain to the target domain. And I have a discriminator trained on the target domain, specialized at differentiating at the target domain, whether the images are real or fake. That would be the common idea. CycleGAN just double this process by introducing a symboling GAN, which will remap back your generated image from the target domain to the source domain and ensure that the mapped back image into the source domain are still indistinguishable with other source domain images. So I first map the source domain to the target domain and do a discriminator on target domain. And then it was mapped back again back to the source domain and ensure that's still indistinguishable. What's the benefit by doing that? It ensures that you cannot lose too much information or diversity in the domain translation process, because that implicitly enforces a reconstruction loss in the whole process. After this mapping and mapping back, you still reconstruct something useful, something aligned with the original information. That ensures there is no collapse and no significant information loss. I find that a very creative idea. So with this dual, so in this way, we have a dual generator and a dual discriminator. So one G and one D for each domain, and we have two domains. So it learns without the need of paired data, because again, map on a distribution level, not a sample-to-sample correspondence. So the result has been amazing. Here are some papers in the original CycleGAN, and now we are able to do much better. Like we can now do multi-domain translation so we can do more than two domains. Like one image, we can make it look like Monet, Van Gogh, Simon, and Euclid, and we could do more. We could do that to a very high resolution as well. Now I think the image translation can be easily done on 1,000 by 1,000 pixel as well. So many beautiful results that you can easily find from website, like changing animal type, changing weathers, changing colors, changing the artistic style, a lot of them, and a lot of commercial applications for entertainment apps. So for image processing, GAN has been such a blessing. And there is a reason, because particularly before image processing tasks, we usually use signal level restrictions. And as I said, PSNR or other reconstruction-driven objectives are really not good descriptions of image reconstruction quality, because humans do not look at the digital pixels. Humans, the perceptual response is highly nonlinear. And there has been a lack of good metric how to judge whether an image is a good image to human ear. It's a subjective issue. And my now colleague, Dr. Alan Bowick, is a world level colleague leader in this aspect. So, but that's still a very difficult topic. But using GAN, we are easily finding a detour for that problem. We no longer require the generated image, for example, for the generated image to be the same as any target or reference image. We just need all those target images to come from an indistinguishable distribution from all the real images from the following the same high quality standard we want them to be. So as a result, there are more flexibility. We could let the discriminator decide what matters about this enhancement or marking process without specifying MSE or other analytical function. That in image processing and image enhancement has led to widespread success. For example, in super resolution, a classical task, we are trying to upscale the resolution, the resolution of the image. And I invite you to compare the three groups of images. So the right column is a ground truth with a lot of textures and with zoomed in regions. So the first, the left two are two successful models by using GAN for super resolution, called super resolution GAN and enhanced super resolution GAN, respectively. And you can see that they are both doing an amazing job, and especially in ESR GAN, they can already reconstruct very natural looking textures at different regions. Well, if you ask me to compute the PSNR or MSE of the two images, they are not necessarily good, I have to say. If you look at the patterns of those hairs, you see those generated hairs look like to have different patterns from the real ground truth. But if you are a person and you look at the image in the middle, you don't find them in any way annoying, right? They also look a natural image, and you don't find this different generation on details very troublesome. That's the extra flexibility enabled by GAN-based image processing. And this more perceptual-driven and less signal-driven idea has seen a lot of success in other applications too. Like there is a famous open source project called de-odify, doing application called image colorization, also using GAN. So by old photos, now you can make it into older black-white photos, and now you can create a new color photo, and that can now be done in older videos. Like I have seen many good demos on YouTube saying how they reconstruct videos taken in the Paris or Beijing city more than 100 years ago, and now make them look colorful and vivid. Really good. And we have been actively working in this field as well. So one of my favorite work in this field done by my PhD student, Yivan Jiang, is called Enlighten GAN. So we are the first to introduce unpaired GAN training into the light enhancement and use many tricks to make it practical work well. So if you look at all the columns, so columns 1, 3, 5 are the input images to our model, pre-trained model, without adding bells and whistles, without tuning any parameter, just using one fixed model, they are transformed into models in the column, into the photos now in the columns 2, 4, and 6. So this is just hardware-free and beautiful, and I really like this work. So it's on all the code and models are on our GitHub. Feel free to check yourself. And I just want to highlight that it has been recently adopted in the standard Python image processing box, open source box called GIMP, and it has become now the standard plugin algorithm for light enhancement. So now there are some links on website you can welcome to check. They made that open source organization made some nice demo videos for our algorithm as well. And a similar extension, the similar works that we have done extended to, for example, deblurring. This is from our another good impact work called DeBlagan V2, now also a standard algorithm in this field. And underworld enhancement, and so to converting the undersea images into human visible images by doing color distortion correction. So there are also, this is done by my student Junru, and this is done by my PhD student Zhenyu. And we are also doing, so GAN can also be working towards many artistical creation tasks. Like this work, we are using pixel to pixel, the pixel GAN, a special variant of cycle GAN, an advanced version of cycle GAN, to do style transfer on texts. This is done in collaboration with Adobe, done by my visiting student Shuai Yang, and now it is in the process of being commercialized by Photoshop. So the thing we can do here is a style transfer, but a transfer a style to a specially structured text like this one. Will just give me this image, give me this text, and I will generate you those text, those stylized like a burning character. And the better thing is you can even control how much style you want to import default to the text. So it could easily be adopted to introduce a GIF, animation style into those texts, generating what we call the dynamic style transfer. And it will look like the text is burning as itself. And now here are more examples. We can transfer fire, we can transfer water, we can transfer smoke, and GAN has been powering all of them. So we have done interactive editing, which will benefit the design task. Also, GAN has been the workhouse here to transform a human sketch, even a very unprofessional sketch, into a high quality design draft in color and good shape like this. This could be done on face, this could be done on product as well. And well, those are all available on our paper list and code to take a look. So we have been utilizing GAN to trans-sensitize the data. So ideally, GAN can generate a lot of data. So if I can really be trained well, GAN could be used to generate a lot of data that we can leverage to trans-supervise the task in domains where training data may be scarce. And because GAN generated data can be controlled by labels, we can even use that to create synthetic label data pairs. This has been first explored by CPR 2008-17's best paper from Apple. They have generated a geometric aware GAN to sensitize the images and do gaze tracking to generate very realistic looking human eye regions. And this file is a GAN image. So we recently also done work in that domain. This is done by my master's student Scott Hong and my PhD student Zhenyu Wu. And they create a hand sensitized model that can use hand 3D geometry as input and output realistically looking hand images that can be used for training hand tracking and hand pose as the recognition models. If you can compare, so all those columns, so this is the input, the pose, and all 3D geometry of the hand. And we want to generate a natural hand looking aligned with this geometry. So all previous results generate heavily blurred, but we created some new GAN structure and can generate it to this aspect. Compared to the real world, I would say that seems to be a good step forward. So all those advanced image processing has led to the widespread concern of deepfake, which means that now you can make a person in a video say or behave something that he or she may never say or speak before. And I guess that is of good popularity. So just to see that we can swap face with persons now with just the open source tools, which of course is a serious threat. And we can even do that in a video domain. Here is a random video I just found from YouTube. And you can see we can do that even with very good temporal consistency, and that can cause many concerns which the community is trying to focus on solving now. There are also, so because GAN has been practically used for so many applications, we have seen a practical demand to put GAN as other neural network in the mobile front end and in the apps as well. Because GAN has now been the standard for super resolution and other artistic creation tasks, so GAN, how to make GAN runs faster and better on mobile devices has involved the desired effort for network compression and acceleration. We have done some effort in that regard. Some of the earliest effort, like now we could compress those GANs with perhaps tens to even hundreds of times smaller sizes and float numbers and make them practically run on your mobile phone. And those are done by my PhD student Haotao Wang and during his internship in Kuaishou. And I believe now this has already been running on the back behind Kuaishou's stylization app. If you are using Kuaishou's style filters, those algorithms are already in function in that mobile app. So GAN could be used for semi-supervised learning due to its ability to generate and sensitize the data. GAN could also be used as a new way to describe the natural image manifold because it can generate images, then based on our assumption, synthesized by analyzed by synthesizer. So GAN itself could be treated as a prior to describe the natural image manifold. And based on that, we could construct many regularizers to our original analytical image reconstruction model, which I'm skipping due to time concerns, but welcome to ask. So many of those works come from my now colleague, Dr. Alex Demarkis, use generative models as a regularizer. And eventually, on my last page, I want to say, GAN, although due to my own background, I'm mostly using the examples from the image domain, GAN is really not developed. But looking at it's a probabilistic model. Well, it has been historically most popular in image field, but really there is no reason it can only be used in image. Like there are great works designing biomolecules and bioinformatics component using GANs. For example, I'm aware my respected colleague, Dr. Yang Shen in EC department has using GAN to generate, to do drug discovery and generate new proteins. I'm also aware of new frontier works using GAN to generate text, generate speech, and even use GAN to synthesize a reinforcement learning policy. Those are all possible. So I just want my last message conveyed to the audience is that don't consider GAN just something to generate a fake face. GAN is really a powerful probabilistic model, practically very powerful, and not restricted to any specific application. So I guess that concludes my talk. We have this awesome model, crispy result, but it's hard optimization, stability issues, and many open theoretical questions. You need to understand the tricks and modification to make it work well, but we are firmly believing in the promise of this field. This is a rising field with a lot of work to do, and I hope today's talk will be a welcome message for you to enter this field. That concludes my talk, and sorry for overkilling the time a little bit. So I'm done.